In this video, we're going to be solving rotational kinematic energy problems. So down here we have our illustration and here we have our question. Below right is a solid disk of mass 1.8 kilograms and radius 18.9 centimeters. The hanging mass of 350 grams is released from rest. Assume the bearing in the rotating disk is frictionless. What is the velocity of the hanging mass after it has fallen 96 centimeters? So what we have is we can write down all the things we are given. M is equal to 0.80 kilograms. For our hanging mass, we have and we need to convert to kilograms. For our drop distance, h, that will equal in meters to 0.930 meters. And of a solid disk is going to be 1/2 mr squared. We want the hanging mass velocity. We know that this is going to be a frictionless bearing. So for our hanging mass, downward we have mg, upwards, I'm gonna write this here. Up we have t. Since we know that it accelerates downward, that means that mg is going to be greater than t. So this is going to be a longer arrow. Now, with Newton's second law, now we want to do the FBD of the disk. So we know that for the disk, we have the tension that's going to cause the torque. The tension is going to wrap around the disk. And it's frictionless. So our torque is equal to the tension force times the R. Torque is equal to moment of inertia times angular acceleration. And then we know that the string does not slip. The condition for that is that linear A is equal to angular acceleration times R. Rearranging that for angular acceleration, A over R, we can substitute that in. And we want to get just T. Now we can plug into Newton's law. So over here we had mg minus t is equal to ma. So we have t now. This is going to be Now what we see is we can factor out our A after we just get mg. Mg is equal to after this, you can substitute in your moment of inertia. So our moment of inertia is 1/2 mr squared. And we have I over here. So you have mr squared over r squared. That's going to cancel. So you have A 1/2 m. But we want to just get A. So A is going to equal to whatever we get from dividing both sides by m plus 1/2 m. Now we have to plug in with our units. So we have our units up here. So we can plug in. This is going to equal to 0.350. That's going to equal to if you plug into your calculator. Now after this we have to do kinematics to get our velocity. So we know that it starts from rest. Therefore we have as our equation, so we can plug in. We just found our acceleration and our height we were given. That is how you get your V. That is for part A. Now, for part B, what if 10% of its initial energy is lost to friction in the disk's bearing as it falls? What would be its velocity after 93 centimeters then? So, if 10% of its initial energy is lost to friction, that means that 90% of gravitational energy becomes kinetic. So, we can represent this as this. So that's only so we know that since omega is equal to V over R, we can substitute that in here. Now after this we can factor. We have 1/2 V squared so we already know that our 1 over R squared is going to equal to 1/2 m, which is 0.900. Therefore, we have this is going to be equal to so after this we have 1/2 times V squared. So we have 0.90 Now, left we have 2.87.625 V squared. 2.87 over V is equal to 2.14 meters per second. 2 masses. We can actually draw this scenario out first. They go through the center of masses. This is going to be your height. Center is O. That is your radius. 2 masses hang over a solid disc pulley with a frictionless bearing as shown. Mass 1 is 8.4 kilograms, mass 2 is 3.2 kilograms, pulley mass is 10.8 kilograms, and pulley radius is 15.4 centimeters. If masses are released from rest, how fast will the hanging masses be moving when they have switched places vertically? The initial separation h is equal to 37.5 centimeters. So that means when this M2 is going to rise up to where M1 is right now, we can actually make this more smaller so that it matches with its size. So what we have is, well, for this drawing, no friction. Oh, here, let's note that no friction. So here, and for our pulley, and in meters, this is 0.14. Now our separation, and it's released from rest. And we know that M1 is so M1 is going to go up and M2 will go down. So important, we need to know that we need to know how far does each mass move. So by switch places vertically, we know that their initial separation is h. To switch places vertically, that means that we have a full separation of 0.375. That's how far they have to travel. So we know M1, which is moving down. The FBD we can draw. We know that M1G is going to be greater than T1 because it's going to be accelerating down. So our longer arrow has to be this one. Let's just draw this on here. We can use Newton's law. M1G has to be the longer arrow. Now let's do mass 2. Down we have M2G. And because it's accelerating up, this means that for this is accelerating down, M2G has to be smaller. Now for Newton's second law, we can write this Now, we can write for the FBD of the pulley. Well, we can just write this with equations. We know that the two tensions will produce torque because they're like this. And T1 and T2 are one string. We know here the moment of inertia is 1/2 mr squared for a solid disk. And we also know that A is equal to A over R. Alpha is equal to A over R. So if we slip these in, we get this from here U divided by R. And you also had an R up here. So those canceled. And you're just left with this. Now we have to solve for acceleration. So we can add the mass equations. So here we have and we can substitute in our torque result. After this, now if we just solve for A, that's our acceleration. Now we have to plug in our numbers. So these were our numbers over there. We have this is going to equal to now after this we can use kinematics. v squared is equal to 2 times acceleration times distance. Taking the root of both sides. That is our velocity. Compare wheels of different shapes. Ring, solid sphere, solid disc, thin spherical shell, rotating and around an axis through their center of mass as shown, being brought to a stop by applying a constant braking force of 41 newtons at the outside edge. Consider all of them to have the same mass of 4.25 kilograms, radius of 15 centimeters, and initial angular speed of 72 radians per second. So, we can draw this out. We have a ring. For our ring, for our solid disc, for our solid sphere, and for our thin spherical shell. We can draw a cut in this. That's the radius. And they're all going to be spinning around. So we're given our radius, initial angular speed, and our braking force at edge. So first we want to find what the torque applied is. Our force was 41. Our radius this is going to be in newtons times meters. And this is going to be constant for all shapes because they all have the same force breaking at edge and the same radius. Now we can find the work to stop. So the work done by torque is going to equal to the change in kinetic energy. This is going to be the change in rotational energy because these objects are rotating and it's not linear motion. This is because it stops. Therefore, we know that only on the moment of inertia. So what is our moment of inertia for our ring? Solid disk, solid sphere, and for the thin spherical shell, now we can find these for each of these respective shapes. Let's start off with the ring. We know that (956) ring is going to be equal to mr squared. This was so for the work, radius is 72. To 48 joules. After we found the work, we can also find the angle distance. So using rotational cake, and since we know that it stops, therefore theta now we have to find what alpha is. We know that torque is equal to, therefore, and if we plug in what our torque is, it's constant, it's 6.15. now we have that theta is equal to negative omega squared. That's going to be 72 squared. .3 rad. But we don't want it to be in rad. We want it to be in revs. It's going to be 6.41 revs. This was the work for part A. Part C, what is the magnitude of the work done by the torque to bring the solid disk to rest? So we're looking at the solid disk now. That will be 124 joules. Now we want the angular distance. We don't want it to be in rad. Now I want to find the for the solid sphere, the angular distance. Theta but we need to multiply this by now onto the Now, after this,